Now this is our next, and you could say our final exercise about Taylor series, left over from last session. We also have an optional little one additionally, but I will not record that one. This one is quite interesting because it's a very famous way of representing Archimedes constant, pi. In German, it's called Kreiszahl, but I guess I didn't find a translation to English. I think it's not called a circle number in the English language. I'm not quite sure. The official term is Archimedes constant. Okay, you know what it is? It's a very famous mathematical constant about circular geometry. And Leibniz himself presented the following, let's say, approximation or representation for exactly speaking, not for pi itself, but for pi over 4. That's interesting because it can be represented as an alternating series, which is constructed by the use of reciprocals of odd numbers only, like this: 1 minus 1/3 plus 1/5 minus 1/7 plus minus, and so on. Always alternating sign. So it's quite obvious that this is derived from a certain kind of power series, Taylor series, whatever. We should find out. And why is it that this obviously convergent series, by the way, due to the Leibniz criterion, it's convergent since it's monotonously decreasing. Its elements are monotonously decreasing by absolute value, but also they are combined with an alternating sign, and also it's a zero sequence inside. So under these three premises, it's well known that by Leibniz test, such a series must have a finite limit value. And as Leibniz tells us, this limit will be pi over 4, 1/4 of the Archimedes constant pi. Interesting. Now, which power series could it be? And I must say, I'm sorry for this. The hint that I gave you here is a little bit misleading. Perhaps it's even not quite correct, because I was using the symbol x null here and also here. Actually, we must take keep these two values apart from each other. I will try and well, correct this little ambiguity here. Well, we should find an appropriate function f first, which has the property that at a certain value of x, here called x1 now, f of x1 equals pi 4. So that we get this as a result of the corresponding Taylor series. That's quite a simple idea. But now, after expanding this respective function to its Taylor series, and then beforehand deciding at which value of x we construct this Taylor series, the hint should be to insert that value of x into the series where the function takes the value of pi over 4. So we must keep apart this x1 from this so-called expansion point x null. You will see, and this is another hint by myself now, use 0 for the expansion point just because this is the standard choice, and in most cases it's also the most convenient, most convenient choice to find a power series. Now, this is also or already sort of a solution to the question, which of our well-known functions has the property that it takes on the value pi over 4 at a certain position? And then remember the following. First, tangent of x equals sine of x over cosine of x. That's well known. Also, this angle of pi over 4 is very famous for being the special angle which you will find in any isosceles and also at the same time rectangular triangle, which you see here, right? This is a triangle which has a right angle at one position. So, and if it's isosceles, means that these two sides connected by the rectangle, by the right angle, have equal length. It means that the other two angles must be pi over 4. For easy reasons, you know that the angle, yes, the sum of all angles in the triangle is always 180 degrees, or better speaking, pi, which is the radians measure of a straight angle. So it's very clear that we have pi over 4 here and here. So this is just a recapitulation of simple trigonometry for you. So what do we find? We find that for this reason, the sine and the cosine of this angle must be the same, because the side opposite to this angle, G, in German it's called G, Gegenkathete, has the same length as the side adjacent to this angle, A, unkathete. Since these cathetes, or these sides, have the same length, it means that sine and cosine must be the same, and also that tangent of x, if I use pi fourth for the variable x, must be 1. The direct reason is that the ratio between the side opposite and the side adjacent to this angle have both, it must be 1, because these sides have equal length. So that's clear. I hope it's really clear. All you have to know, or the most important thing you have to know about tangent of x, perhaps three properties. Firstly, it contains the origin, so that tangent of 0 equals 0. Secondly, it's an odd function, also quite as odd as the sine of x. Both are odd, while cosine of x is an even function. And thirdly, the tangent of pi over 4 equals 1. So that's what you know. And now, the other way around. Since we are looking, we are not looking for a function which has 1 as a result, like it's given here. Instead, we want the function value to reach pi over 4. So what do? We just take the inverse function, the inverse tangent. Okay, so that f of x will be the inverse tangent of x. That's a good idea, at least. Now, once again, tangent of pi over 4 equals 1 means that the inverse tangent of 1 must be pi over 4. So this will be our function, and we will expand this to its Taylor series at x null equals 0. That's the most simple idea. And now it's a little bit of work, but well, it's not so serious, really. Let's go ahead. And this is my notation, you know, Taylor series at 0 of x. What is it? Well, I take the first derivative. You all may know, or should know, from a handbook, from your integration or differentiation tables, that the first derivative of the arctan, as I may say, arctangent, which is the official term for the inverse tangent, equals this interesting rational function, which is 1 over 1 plus x squared. Now, this can be taken into the usual way, into potency notation, power notation. So it's the same as 1 plus x squared, this quantity to the power of -1. Let's proceed. We need the second, the third, and so on derivative. The second derivative will be, by the usual rule, potency rule for differentiation. The -1 gets a factor here, and then the exponent is reduced by 1. It gets -2. The argument stays the same, but please remember this is a case for using the famous chain rule. The chain rule says we must take the inner derivative as a factor, and the inner derivative, since 1 is an additive constant, it goes away, it disappears, it vanishes. And then Here, the derivative, of course, is 2 times x, linear factor. So that's it. But now we have a product, and it's a case for the product rule in the next step, or even for the quotient rule. The quotient rule, I think, or ratio rule, we haven't even used by now. Have we? Oh, yes, we have, but only once. So generally speaking, u over v differentiated equals, as you know, fraction line. The denominator is the square of the original denominator, v squared. And in the numerator, you get this cross derivative, you could say, with a minus in between. So I recommend to remember in alphabetical order, u is differentiated first, taken times v, and then minus vice versa, u times v prime. So that's it, yeah? Now let's use it in, or first of all, let's put this in fraction notation again. So we have, here's the -1 from, you know, it came from here, from the exponent. So we have negative 2x in the numerator, and then over this parenthesis term 1 plus x squared, altogether squared. That's it. Now please be careful, because the denominator term is already squared, which means by using this scheme, we must square it again. So in the end, we get parenthesis 1 plus x squared, closing parenthesis, power 4, instead of power 2 here. This is v squared. Now let's take u prime, which is numerator term derivative. Linear term -2x gets -2 as a derivative, times v, and don't forget this parenthesis term squared. This is our v. I put it here. The outside square is important. And then I go on with minus u, just take over u, negative, you look here, minus, and then -2x. U is stays as it is, and then multiplied by v prime, which is this time this parenthesis squared differentiated. So let's use the chain rule again. Exponent of 2 gets a factor, here it is, 2 times, then parenthesis term to the power of 1, so just this term. And then don't forget again to take the inner derivative by the chain rule, following the chain rule, which is again a factor of 2x. So that's a little bit complicated. Now, it takes a little while to proceed and then to find the scheme. I would like to abbreviate this a little bit at the moment. So let's find out which are our values of the diverse derivatives at our expansion point, which is 0. Let's insert 0 for x. Firstly, in the function, of course, as I told you before, f of 0 equals inverse tangent of 0, and this is 0 since it's a odd function, and we all know that the tangent of 0 equals 0, so also the inverse tangent of 0 must be 0. That's 0. The first derivative, f prime, takes on, look here, if I insert x equals 0, I have always this parenthesis term, which appears almost everywhere, gets equal to 1. Okay, 1 plus 0 squared, so 1. So I have, well, 1 over 1, which is 1 for f prime at 0. And f double prime of 0 will be 0 again. And that's because, looking here, this has already been our second derivative of the inverse tangent. Oh yes, we proceeded to the third one, as I see here. This was, sorry, I forget to tell you, this is f triple prime, of course, which we constructed here. But this is f double prime. And then inserting 0, we get 0 in the numerator. And importantly, the denominator stays unequal to 0. So we have 0 over non-zero, which is always clearly equal to 0. It's not the case for any kind of limiting procedure. This is what I'm trying to say. Now, f triple prime, on the other hand, gets, let's look here, this is 1, neutral. Also here, 1, 1. So I get -2 times 1 minus, now look here, minus, minus, and this is about, this is a 0, so it's a factor of 0 again. So this, everything behind here disappears. On the other hand, I have 1 power 4. So it's all that stays is really is this -2. So -2 is the result. And now please allow me to abbreviate a little bit, because it turns out, it's quite an effort to do, but it turns out that you get an alternating way of building up factorials at this position. No, it's not true. Actually, it's a little simpler even. By you would have to draw these terms together and then simplify the whole thing. And in the next step of taking derivatives, you will find that an according factor will appear, which is a little work to do to prove this. But just believe me the following. You will find by the Taylor formula, which always takes the nth derivative at 0 in our case over n factorial, you will find, let's start out with this element number 0. The constant is 0, that's clear. The pure constant will be 0, but the linear term gets this 1 inserted here over 1 factorial, that's also simple, times x. So our linear term will just be plain x. Here it is. That's the first real element of the series in the end. But then the squared, yeah, you see, plus 0 means every second contribution gets 0. Now I'm here, so it also gets clear at right now that all the elements which remain are odd elements. All the even elements disappear. That's quite easy. But now take this element number 3, f triple prime of 0 equals -2. So I have -2 over 2 factorial. No, sorry, over 3 factorial. And that means that actually, in this case, from below, this one cancels against this, so that the highest factor stays in the denominator, which is 3. Let me go back to this idea proceeding here. Taking the 5th and 7th and so on derivative, you will find that it's true what I first thought. You will always have a certain factorial remaining in the numerator. In this case, it's -2 factorial. In the next case, for f number 5, okay, derivative number 5 of x, you will have +4 factorial. And then inserting here, +4 factorial over 5 factorial, again, the numerator term cancels, and the largest factor in the denominator stays, which is 5 in that case. And in the next case, it will be negative and 7 below. You see, you just believe me, it's quite an effort to show this formally. So what remains is really this alternating series with only odd elements, which are x minus 1/3 times x power 3 plus minus alternating series. The next element would be 1/5, a positive 1/5 times x power 5 and so on. And now that's why it makes sense to insert x equals 1 this time, which we called x1. Okay, let's call it x1 again, like in my modified hint here, where we found out that this is a good starting point for the whole procedure. And then inserting 1 for x, we find that all these power terms get neutral. They get 1, 1 power 3, 1 power 5, and so on, always 1. And all that remains are these alternating reciprocals of odd numbers in the form of 1 minus 1/3 plus 1/5 minus 1/7 and so on. And that's, you can say that's the proof, since we know that this series, we would have to prove again that it converges for any value of x, but quite surely it converges for 1, which is very near to the expansion point. I think it should be the case that the convergence radius of this series is even approaching infinity. I'm not 100% sure, but relatively sure. and this was not part of the exercise. But anyway, since it converges, it must converge to the function for which it was constructed. And so in the end, we have shown that this interesting alternating series of reciprocal odd numbers equals pi over 4. Sorry for the a little complicated explanation, since there was a step where we just got a little stuck deciding not to go into more detail. Thank you.